This next section we're getting into is going to be talking about electric charges, the forces that these charges exert on each other. We're not quite yet going to be talking about current, like the flow of charges through wires, but just charges in general. So you may or may not know there are two fundamental charges or types of charge. Protons are positively charged, electrons are negatively charged. Benjamin Franklin is the one that defined a positive versus negative, though at the time he did not understand where the positive was in an atom, and perhaps not even the atom, just knew that there were some fundamental charges. The basic charge on a proton or electron is called the fundamental unit of charge. We use a lowercase e to represent this. And I apologize, I'm dog sitting a cute little puppy, and so we have some little background noise. Okay, fundamental unit of charge, that's what this lowercase e represents. A proton has a positive E charge, an electron has a negative E charge. So protons and electrons are fundamentally charged objects. Now, the value of this fundamental unit of charge is 1.6 times 10 to the negative 19 coulombs. Coulombs is the unit we use to represent charge. This value is both within the chapter in the test notes, but it is also on the front page of the test notes where we have constants. This fundamental unit of charge is called that because this is how we break down two individual charges. Now, a couple things you may or may not already know. Any two charges that are similar, they're like, so they're the same, both positive or both negative, they will repel each other. So like charges repel each other, so they push away from each other. Opposite charges attract each other. And that is what binds the electrons to the nucleus in an atom. All atoms are made of protons, neutrons, and electrons. In the very center, the nucleus, there are protons and neutrons. And these are bound together by very strong nuclear forces, which we're not going to talk about that at this point. So in the nucleus, we have protons and we have neutrons. The protons are positively charged. The neutrons are neutral. So neutrons are neutral, meaning they are not charged. Outside of the nucleus, there's electrons in these orbital clouds, these orbital regions where the electrons in general reside. We can't pinpoint an electron, but we have a definition of in general where they reside. And so the electrons are experiencing an attractive force towards the nucleus because they have opposite charges to the nucleus. The electrons are negatively charged. So opposite charges attract, like charges, similar charges repel. So the protons themselves in the nucleus are repelling, but there's other nuclear forces that are stronger than the electric force at those very close distances and hold the nucleus together. All right, so charges, we have protons, we have electrons. As we talk about charging an object, whether an object as a whole is charged or not, all we mean is that there's an imbalance of protons and electrons. A charged object has an imbalance of protons and electrons. So either there's more electrons than protons or less electrons than protons. To charge an object, we're always either adding electrons somehow or removing electrons. We cannot remove the protons from the nucleus without some, particle accelerators, some serious energy. So in our everyday world, if we talk about charging an object, it means we have either added electrons or removed electrons from the object. So a common example is to rub a plastic rod with fur. If I have a plastic rod and I rub it with fur, this rubbing action is putting energy in the system, and it's causing enough energy to break some of the electric forces of the electrons with the protons. In this case, electrons, not all of them, but some electrons from the fur move to the rod. Electrons move from the fur to the rod. And this is only some. So when we have rubbed our plastic rod and we just rub fur along it, it works with, I think, wool. I don't know that I'm saying that correctly. The fur will have given up some of its electrons, and thus the fur will have a net positive charge. Now, both the rod and the fur still have their same number of protons they started with. The fur now has fewer electrons, and the rod has more electrons. And so we say the rod is positively charged, and the fur, oh my goodness, totally just kidding. Sorry about that. The rod is negatively charged. It has excess electrons. The fur is the one that is positively charged. Now, the number of fewer electrons, the number of electrons that left the fur are now on the rod. So there's a specific number that will have transferred. And this rod could be used to charge something else. It could be used to attract. If I have a small metal ball and I bring this rod nearby this small metal ball, the ball will actually be attracted. Even though, let me clarify, this ball is neutral, meaning the same number of electrons and protons. It does not have an excess of either one. The ball, though, attracts to this rod because metal is a conductor. So that's a term we're going to mention as well. A conductor easily shares its valence electrons, its outside electrons. And what I mean by that is the electron, those outer valence electrons, do not need to stay with their specific atoms. So these valence electrons are shared between all the neighboring atoms, and so they can easily move. That is what we mean by a conductor, is the electrons, specifically the outer shell electrons, can easily move throughout the metal object, throughout this conductor. So if I come back to this metal ball, what's going to happen is some of those valence electrons are going to move over to the left side because they are being repelled by this ball. That leaves a net positive charge on the right side because some of the electrons from those atoms move to the left. But notice, if I add up the positive and negative I have drawn, it is still neutral. I drew 4 negatives on the left, 4 positives on the right. Because there has not been any contact between the ball and the rod yet, that ball is still neutral. Now, a plastic rod is considered an insulator. The electrons stay with their atoms. They do not easily move from atom to atom. And so this plastic rod, we can totally charge it. We can get the negative charge on it, but that negative charge is not going to move around on the plastic rod. It's going to stay where we rubbed the rod and charged it. All right. In this metal ball right now, so we have, there's been no contact yet between the rod and the ball. Between ball and the rod. When we get this separation of charge in here, this is polarization. The charge is becoming polarized, meaning one side of the ball is now negative, the other side is positive, though overall the ball is still neutral. Okay. I'm going to post some videos about charging so that you can also have a visual of this, but we'll get those up as well. Now, in this situation, because there is an attraction, this ball is now very much attracted to the rod. So that says attracted. It's hard to read. And that's because this positive side now is close to these negative charges, and opposite charges attract. In an experimental situation, if I do this ball actually, the attraction happens very quickly. So now, when the ball contacts the rod, so this ball is going to contact the rod. Now remember, I'm just going to draw the same number of protons and electrons here. That separation of charge. As soon as there is this physical contact, some of these electrons are going to physically move from the rod to the ball. Okay, so this contact, we call this conduction. The rubbing the fur on the rod is a type of conduction as well. Any type of physical contact that can allow the charges to move over is considered conduction of sorts. So now, as soon as this happens really quickly, but as soon as some of these electrons jump on the ball now is repelled from the rod. And it pushes itself away. Well, it gets pushed away, I should say. So we have this ball, and it's now pushing away from the rod. And that's because, if we think up here, these electrons, the same number of electrons that there are appearing to be protons there, are jumping on. So we have these 4 electrons over here. An electron jumps on for every proton I had drawn on the right. So if we added up all these positive and negatives, we have a net negative 4 electrons, just based off of the way I've drawn the picture. So this ball or sphere now has a net negative charge. It has more electrons than protons. And so now we have two negatively charged objects which repel. They repel because now they have the same overall net charge. Not magnitude, just that they're both negatively charged. So we can easily charge an object by rubbing. So in this example, fur rubbed on plastic of some sort, the fur loses electrons to the plastic, and the fur becomes positively charged, the plastic becomes negatively charged. Another common example would be silk rubbed on a glass rod, or just on glass in general. It is known that silk becomes negatively charged and the glass rod becomes positively charged. So these are 2 you want to keep in mind. These are known in terms of which object becomes positively or negatively charged. That means if I brought my glass rod that now has this net positive charge near a sphere, again, this metal sphere is neutral, but because it is nearby these positive charges, some electrons are going to be attracted to that side, leaving the opposite side positively charged. It is still neutral, but the charges now are polarized because the charges are separating to both sides of the sphere. And this metal sphere would attract to this rod, just like it did before it was attracted to the negative rod. So it doesn't matter whether the rod is positively or negatively charged. If the metal sphere is neutral, the fact that it is metal, it's a conductor, the electrons can easily move. And they will move to whichever side of the sphere is, the electrons will move to either closer to the positive rod or farther away from the negative rod. So this metal sphere, because it is a conductor, is going to attract. As soon as it does make contact with the rod, so let me draw this out, contact. Now we want to be careful here. We have this separation of charge, remember. There's no specific reason I've drawn 4 electrons and protons. The amount it separates by is going to depend upon the material and how strongly charged or how much charged the rod is. But here, electrons are going to leave the ball and jump to the rod. It's only electrons that can move from object to object. The protons are tightly bound in the nucleus. And so this, because some of the electrons leave and jump to the rod, this sphere now has a net positive charge. And it will be repelled by this rod. Okay, the rod will have fewer protons. Now, okay, let me rephrase that. It has the same number of protons it started with, but it has less of a net positive charge. Because some of the electrons transferred from this sphere, this metal sphere or ball, to that rod. That would be the same as over here when we were dealing on the left side where we were dealing with a negative rod. I didn't really represent that. I should represent that on my rod, that it now has fewer negative charges. It still has a net negative charge, but it is smaller than it was before because some of the electrons went to the ball. All right, so keep in mind these two situations. Silk with glass, the silk becomes negatively charged, the glass becomes positively charged. Fur with plastic, fur becomes positively charged, plastic becomes negatively charged. And it doesn't have to be, it could be plastic, rubber, anything along those lines. So conduction is a term that we will often see that also represents this rubbing one surface along another. If you've ever rubbed a balloon on your hair, oops, that's not how you spit a balloon, and stick to the wall. My hair doesn't do this very well, but some people, it works very well. You actually can get the balloon sticking to the wall. Now, if we think about these materials, fur and plastic, silk and glass, well, balloon is a rubber, it's plastic, it's along those lines. Our hair is along the lines of, it's not the same thing, I know, as fur, but it's along the same line. If we rub a balloon on our hair, the balloon, wherever we rubbed it, ends up with a negative charge. So with me drawing the negative charge on the right side here, that assumes that I rubbed this side on my hair. When we bring that up to the wall is an insulator. It's not a conductor like the metal sphere we were talking about before. Both the balloon and the wall are insulators. So what happens is the atoms, the actual individual atoms, The electrons, some of the valence electrons in these atoms, move to the far side of the atoms, leaving the left side of the atom positively charged. These atoms become polarized. And this attractive force between the negatively charged balloon and the positive side of the atoms is stronger than the, not by much, but it's a little bit stronger than the repulsive force with the electrons on the other side. Now, the balloon won't stay there forever, and that's because air is a fairly decent conductor, and the electrons will slowly move to the air and then ground. Electrons are always trying to get as far away as possible. They repel each other because they are similarly charged. So ground is essentially the farthest they can get away from each other. And if there is a path, then we can, that's where the electrons will go. All right, so for charged objects, the symbol we use to represent the net charge on the object is a Q. I'm not entirely sure why. Lowercase q, capital Q, doesn't matter. Either one represents the net amount of charge on an object. It is measured in coulombs. This net charge is going to be either an excess number of electrons or a fewer number of electrons. So it'll be some multiple of that fundamental unit of charge. Okay, I'm going to post a couple videos showing conduction and induction because I think that can be helpful as well. Charging by induction, just to give an example, so induction is another way of charging. Let's go back to that example of the sphere that we had held close to a negatively charged rod. So the charges in the sphere, some of the electrons get repelled to the other side. So this is a metal sphere or ball of some sort. If, while I have this metal sphere, if I touch this side and ground it, and the symbol right here is a symbol we use to represent ground. By me touching it, I'm providing a path for electrons to move through my finger, down my arm, down my feet to the ground. And so electrons, these excess electrons, pass through me to the ground. The result will be this sphere has now lost these excess electrons, and so it has a net positive charge. This excess electrons passing to ground is called discharging. I'm allowing these electrons to be removed. They leave that sphere. Now, not all of them. Please understand that. It's just these excess ones on the left, or what appears to be excess because of that polarization that transfers to the ground. That's discharging, removing charge. That leaves us with this net positive charge. This process, even though there's still touch, the process is called charging by induction because we had to first bring this rod nearby to cause the polarization on the spheres. So I'm going to post a couple of videos, and there's going to be a couple of them showing charging by conduction, the rubbing a rod with the fur or silk, as well as by induction. And they show different ways of charging by induction.